the discovery that broke the universe. How astronomers discovered the universe is accelerating and why this should be impossible. For most of human history, the universe was assumed to be static, eternal, and unchanging on the largest scales. Stars moved, galaxies rotated, but the cosmic stage itself was believed to be fixed. This assumption survived not because it was proven, but because no observational tool existed that could challenge it. That changed in the early 20th century, when astronomy transformed from cataloging objects into measuring the geometry of the universe itself. In 1929, Edwin Hubble made a discovery that permanently altered cosmology. By measuring the redshift of distant galaxies, Hubble demonstrated that the universe is expanding. Galaxies are not simply moving through space. Space itself is stretching, carrying galaxies with it. The farther a galaxy is from us, the faster it appears to recede. This relationship, now called Hubble's law, established that the universe had a dynamic history and likely began from a much denser, hotter state. Once expansion was accepted, a deeper question immediately followed. What is the expansion doing over time? Every known force of nature suggested a simple answer. Gravity is attractive. Matter attracts matter. If the universe is expanding, then the combined gravitational pull of all matter and energy should be slowing that expansion down. The universe should be decelerating, like a ball thrown upward against gravity. For decades, cosmology operated under this assumption. The debate was not whether expansion was slowing, but how fast. Scientists argued over the density of matter in the universe and whether gravity would eventually halt expansion entirely, leading to a collapse, or merely slow it enough to approach a quiet, frozen state. These were measurable questions, at least in principle. What was missing was a reliable way to measure cosmic deceleration directly. To measure changes in expansion over billions of years, astronomers needed objects that could act as precise distance markers across vast cosmic scales. This is where Type Ia supernova became critical. These stellar explosions occur when a white dwarf star accumulates enough mass to trigger a runaway nuclear reaction. Because this process happens at a nearly fixed mass threshold, Type Ia supernova explode with remarkably uniform intrinsic brightness. This makes them standard candles objects whose true luminosity is known, allowing their distance to be calculated by how dim they appear. In the 1990s, two independent research teams began using Type Ia supernova to probe the expansion history of the universe. One was the Supernova Cosmology Project, led by Saul Perlmutter. The other was the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Their goal was straightforward: measure how much the expansion of the universe has slowed over time due to gravity. The logic was simple. If the universe is decelerating, distant supernova whose light began traveling toward us billions of years ago should appear brighter than expected. This would indicate that the universe was expanding faster in the past and has since slowed down. The data should reveal a cosmic braking effect, but when the measurements came in, they showed the opposite. The distant supernova were dimmer than expected. Not slightly dimmer, but consistently and significantly so. This meant they were farther away than they should be if the expansion were slowing down. The only explanation consistent with the data was that the expansion of the universe has been speeding up over time. At first, the result was treated with extreme skepticism. Extraordinary claims require extraordinary evidence, and an accelerating universe directly contradicted everything cosmologists believed about gravity and large-scale structure. Researchers checked for dust that might be dimming the light, systematic errors in measurement, evolution in supernova behavior, and instrumental biases. Independent observations were repeated. Different telescopes, different teams, different analysis methods. The acceleration remained. By the late 1990s, it became unavoidable. The universe is not slowing down, it is accelerating. Something is overpowering gravity on the largest scales of reality, pushing galaxies apart faster and faster as time progresses. This discovery did not merely add a new component to cosmology, it shattered its foundation. According to known physics, there is no mechanism that can produce large-scale repulsive gravity under normal conditions. All familiar forms of matter and energy, stars, gas, radiation, dark matter attract. None can drive acceleration. To make the equations work, cosmologists were forced to introduce a new term, a form of energy inherent to space itself, with negative pressure strong enough to drive accelerated expansion. This unknown component was given a name that reflected ignorance rather than understanding: dark energy. Dark energy was not detected in a laboratory. It does not emit light. It does not interact with matter in any known way except through gravity. Its existence is inferred purely from its effect on the geometry of the universe, yet it appears to dominate cosmic dynamics, accounting for roughly 70% of the total energy content of the universe. The implications were profound. If dark energy is constant, acceleration will continue forever, isolating galaxies and freezing cosmic structure beyond observable reach. If it changes over time, the fate of the universe could be far more dramatic. But at the moment of discovery, none of this was known. What was clear was that cosmology had crossed a line. The universe was no longer governed only by matter and gravity. It was being shaped by something deeper, a property of spacetime itself that modern physics could not explain. This discovery did not answer questions. It created them, and it forced scientists to confront a reality that had never been anticipated. The dominant force in the universe is something we do not understand, cannot directly observe, and may never be able to control. In the next section, the question becomes unavoidable. How can we be sure this acceleration is real and not an illusion created by our measurements? Section 2, Measuring the Invisible. How scientists proved cosmic acceleration is real and eliminated every alternative explanation. Once the idea of an accelerating universe was placed on the table, the burden of proof became extreme. A claim of this magnitude could not rely on a single method, a single dataset, or a single assumption. If the acceleration was an illusion created by flawed measurements, misunderstood astrophysics, or observational bias, it had to be exposed. Cosmology entered a phase of aggressive self-interrogation, where every link in the observational chain was tested. At the heart of the problem was a fundamental limitation. Cosmology cannot perform experiments. Scientists cannot manipulate galaxies or rewind cosmic history. The universe offers only one dataset, observed from one location, at one moment in time. This makes measurement strategy critical. To confirm acceleration, independent techniques had to converge on the same conclusion. The first pillar of evidence remained Type Ia supernova, but their use demanded unprecedented precision. Although these supernovae are remarkably uniform, they are not perfectly identical. Subtle variations exist in their light curves, how brightness rises and falls over time. In the 1990s, astronomers developed calibration techniques that corrected for these variations, using empirical relationships between peak brightness and decay rate. This allowed distances to be measured with accuracy across billions of light years. But even with calibration, skepticism remained. One concern was interstellar dust. Dust can absorb light and make distant objects appear dimmer, mimicking the effect of acceleration. To test this, astronomers measured supernovae across multiple wavelengths. Ordinary dust redens light in predictable ways. The dimming observed did not match dust signatures. Exotic gray dust was proposed, but it would require fine-tuned properties and still conflicted with other observations. Another concern was cosmic evolution. What if distant supernovae were fundamentally different from nearby ones, because the universe was younger? This possibility was tested by comparing supernovae across different host galaxies, environments, and redshifts. No systematic evolution sufficient to explain the acceleration was found. The signal persisted across independent samples, yet supernovae alone were not enough. Cosmologists needed an entirely different ruler, one not based on stellar explosions, but on the structure of the universe itself. This led to the second pillar, the cosmic microwave background. The cosmic microwave background, or CMB, is relic radiation from approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could travel freely. This radiation fills the universe uniformly, carrying tiny temperature fluctuations that encode information about the early universe's geometry and composition. Satellites such as COBE, WMAP, and later Planck map these fluctuations with extraordinary precision. The angular size of the temperature patterns revealed the overall geometry of space. The result was striking. The universe is spatially flat to a very high degree of accuracy. Flatness alone does not imply acceleration, but it creates a constraint. Measurements of matter, both ordinary and dark, showed that matter accounts for only about 30% of the energy density required for flatness. Something else must supply the remaining 70%. This missing component behaved exactly like dark energy inferred from supernova. A third, independent probe soon reinforced the conclusion: baryon acoustic oscillations. In the early universe, matter and radiation were coupled in a hot plasma. Pressure waves propagated through this plasma, leaving behind a characteristic scale, a preferred separation distance between galaxies. This scale acts as a cosmic ruler embedded in the large-scale structure of the universe. By mapping millions of galaxies, surveys such as the Sloan Digital Sky Survey measured this acoustic scale at different epochs. The way the scale stretches over time depends on the expansion history of the universe. The measurements independently show that expansion has accelerated in recent cosmic history. At this point, three unrelated methods, supernova, the cosmic microwave background, and large-scale structure, all pointed to the same conclusion. Acceleration was not an artifact, it was a geometric fact, but cosmologists continued to push further. Gravitational lensing provided another check. Massive objects bend spacetime, distorting the images of background galaxies. By statistically analyzing these distortions, scientists could map the growth of cosmic structure over time. In an accelerating universe, structure formation slows down because expansion counteracts gravitational collapse. Weak lensing surveys showed exactly this behavior. Structures grew rapidly in the early universe and then slowed as dark energy began to dominate. This matched predictions from acceleration models and conflicted with any universe governed solely by matter and gravity. Even galaxy cluster counts supported the picture. The number and mass distribution of galaxy clusters depend sensitively on the expansion rate. Observations showed fewer massive clusters forming at late times than expected in a decelerating universe. Again, acceleration provided the simplest explanation. What emerged was not a single line of evidence, but a converging web. Each method had different assumptions, different systematics, and different sources of error, yet all converged on the same cosmological model, a universe dominated by dark energy. This convergence is what transformed dark energy from a controversial hypothesis into a foundational component of modern cosmology. Still, a deeper question remained. Measuring acceleration is one thing, understanding its nature is another. All observations describe what the universe is doing, not why it is doing it. The equations of general relativity allow acceleration if the energy content of the universe includes something with sufficiently negative pressure, but they do not explain the origin of such a component. This distinction is crucial. Dark energy is not observed directly. It is inferred as the simplest explanation consistent with geometry, dynamics, and structure. Its properties are encoded in a parameter called the equation of state, which relates pressure to energy density. If this parameter equals exactly -1, dark energy behaves like a cosmological constant, a fixed property of space. Current measurements are consistent with this value, but uncertainties remain. Small deviations could signal entirely new physics. This uncertainty drives the next phase of cosmology. Modern experiments are no longer asking whether dark energy exists. They are asking whether it is constant, dynamic, or a sign that our understanding of gravity itself is incomplete. The precision required is extraordinary. Differences in expansion history of only a few percent separate radically different futures for the universe. Measuring these differences demands surveys mapping billions of galaxies, detecting subtle distortions at the level of 1 part in 10,000. Projects such as Euclid, the Vera Rubin Observatory, and the Nancy Grace Roman Space Telescope are designed for this purpose. They are not searching for dark energy directly. They are mapping spacetime so precisely that any deviation from standard expansion will be impossible to hide. By this point, the scientific position is clear. Cosmic acceleration is not a statistical fluke, not an observational illusion, and not a misinterpretation of astrophysical processes. It is a robust, cross-validated feature of reality. But confirmation brings discomfort, because once something is measured beyond reasonable doubt, physics is obligated to explain it, and dark energy does not fit naturally into any established theoretical framework. The measurements are solid, the mystery is not, which leads directly to the next problem, one that strikes at the core of physics itself. If gravity governs spacetime, why is gravity failing on the largest scales of the universe? Section 3. When gravity failed, why Einstein's theory predicts deceleration and why the universe refuses to obey. At the foundation of modern cosmology lies a single assumption that once seemed unshakable. Gravity governs the large-scale behavior of the universe. Every planet, star, galaxy, and cluster obeys its pull. From falling apples to orbiting moons, gravity has never failed a test. When Albert Einstein formulated general relativity in 1915, he elevated gravity from a force to a property of spacetime itself. Matter tells spacetime how to curve, and spacetime tells matter how to move. General relativity does not merely describe gravity locally. It governs the entire universe. When Einstein applied his equations to the cosmos, they predicted something remarkable: a dynamic universe. Space could expand or contract depending on the energy and matter within it. This prediction came before any observational evidence of expansion existed. But embedded within those equations was a clear expectation. A universe filled with matter and radiation should decelerate. Expansion could begin, but gravity would always act as a brake. The more matter the universe contained, the stronger the deceleration. This expectation was not philosophical, it was mathematical. In general relativity, the expansion rate of the universe is described by the Friedmann equations. These equations relate how fast the universe expands to the energy density, pressure, and curvature of spacetime. For ordinary matter, pressure is negligible compared to energy density. For radiation, pressure is positive. In both cases, gravity is attractive. The equations predict slowing expansion. Acceleration requires something fundamentally different. To cause acceleration, the universe must contain a component whose pressure is negative, not just slightly negative, but strongly so. Negative pressure produces gravitational repulsion in Einstein's equations. It does not pull spacetime inward, it pushes it outward. Nothing in classical physics behaves this way. This is where the crisis began. Once observations showed acceleration, cosmologists were forced to ask whether gravity itself was being misunderstood. Could Einstein's theory be incomplete? Could it break down on the largest scales? Or was something new overwhelming gravity? To understand the depth of the problem, one must appreciate how precisely general relativity has been tested. It explains the orbit of Mercury, gravitational lensing, time dilation, black holes, gravitational waves, and the dynamics of galaxies. Every test within the observable universe except one confirms it. That exception is cosmic acceleration. This makes dark energy fundamentally different from dark matter. Dark matter enhances gravity. It does not oppose it. Dark energy counteracts gravity's pull across billions of light years. It acts uniformly, filling all of space, unaffected by structure or clustering. This uniformity is key. If dark energy were composed of particles like matter, it would clump, but it does not. Its density remains nearly constant as the universe expands. As space grows, the total amount of dark energy grows with it. This behavior is deeply counterintuitive. When matter spreads out, its density drops. When radiation spreads out, its energy dilutes even faster. Dark energy does neither. This violates every instinct formed by classical physics. Einstein himself encountered this problem a century earlier. When he first applied general relativity to the universe, his equations predicted either expansion or contraction. But at the time, astronomers believed the universe was static. To prevent collapse, Einstein added an extra term to his equations, the cosmological constant. This constant acted as a repulsive force, exactly balancing gravity and holding the universe in equilibrium. Mathematically, it worked. Physically, it was artificial. Once expansion was discovered, Einstein reportedly called the cosmological constant his greatest blunder. But with the discovery of acceleration, the blunder returned not as a mistake, but as a necessity. The cosmological constant behaves exactly like dark energy with constant density and negative pressure. In fact, it is the simplest possible explanation for acceleration within general relativity. But simplicity does not equal understanding. The problem is not that the equations allow acceleration. The problem is that known physics cannot explain the value required. Quantum field theory predicts that empty space is not truly empty. Even in vacuum, quantum fields fluctuate, creating temporary particles and energy. This vacuum energy should contribute to the cosmological constant. When physicists calculate this contribution, they obtain a value that is larger than observed by a factor of 10,120, the worst theoretical prediction in the history of science. This discrepancy is not a rounding error. It is an existential failure of theory. Either quantum field theory is catastrophically wrong, general relativity breaks down on cosmic scales, or some unknown mechanism cancels vacuum energy almost perfectly, leaving behind a tiny residue that drives acceleration. None of these options are comfortable. As a result, physicists began exploring alternatives. Perhaps gravity behaves differently on large scales. Modified gravity theories propose changes to Einstein's equations that only become apparent across cosmic distances. These include scalar tensor theories, massive gravity, and extra-dimensional models. But these theories face brutal constraints. They must reproduce general relativity precisely within the solar system, while deviating only at cosmological scales. Many fail observational tests. Others introduce instabilities or violate fundamental principles like causality. Meanwhile, observations continue to support general relativity across vast distances through gravitational waves and lensing. Gravity does not appear weakened or altered. It appears intact but overwhelmed. This leads to an uncomfortable conclusion. Gravity is not failing because it is wrong. It is failing because it is outnumbered. Dark energy dominates the energy budget of the universe. Matter, everything we see, is a minority component. Gravity still works, but it is no longer in control. As the universe expands, matter dilutes. Dark energy does not. Over time, gravity becomes increasingly irrelevant on cosmic scales. Galaxies become isolated, structures freeze. The universe becomes emptier, colder, and more fragmented. This transition is already underway. Roughly 5 billion years ago, dark energy overtook matter as the dominant cosmic component. From that moment on, expansion began accelerating. This timing raises further questions. Why now? Why did dark energy become dominant only recently in cosmic history? This coincidence problem has no accepted solution. It suggests either deep fine-tuning or missing physics. At this point, cosmology faces a choice. Either dark energy is a fundamental property of spacetime, constant, featureless, and eternal, or it is something dynamic, evolving, and potentially controllable. Answering this requires moving beyond gravity itself and into the quantum nature of the vacuum, which brings us to the most dangerous idea ever introduced into physics. Empty space may contain more energy than everything else in the universe combined. Section 4: Vacuum energy, the most dangerous idea in physics. Why empty space may contain more energy than all matter combined, and why this breaks our theories. To understand dark energy at its most fundamental level, physicists were forced to confront a concept that once seemed harmless: the vacuum. In everyday language, a vacuum is emptiness, the absence of matter. But in modern physics, empty space is anything but empty. It is an active, restless medium governed by quantum laws, filled with fluctuating fields that never truly settle to zero. This realization emerges from quantum field theory, the framework that underpins the standard model of particle physics. According to this theory, every point in space is permeated by quantum fields. Particles are simply excitations of these fields, like ripples on an ocean. Even when no particles are present, the fields remain and they fluctuate. These fluctuations are not optional. They are required by the uncertainty principle. A field cannot have exactly zero energy everywhere, because doing so would violate fundamental quantum limits. As a result, even the lowest energy state of a field, its vacuum state, carries energy. This is known as zero-point energy. At small scales, vacuum energy is not speculative. It has measurable effects. One of the most famous is the Casimir effect, where two uncharged metal plates placed extremely close together experience an attractive force due to changes in vacuum fluctuations between them. This phenomenon has been measured repeatedly in laboratory experiments. Vacuum energy is real, but when physicists attempt to calculate how much vacuum energy exists throughout the universe, the results become catastrophic. Quantum field theory requires summing the zero-point energy of every mode of every field at every point in space. Even when conservative assumptions are made, cutting off calculations at energies far below the Planck scale, the predicted vacuum energy density is enormous. If this energy gravitated normally, as general relativity demands, the universe would not merely be accelerating, it would have torn itself apart almost instantly after the Big Bang. Space would expand so violently that galaxies, atoms, and even spacetime itself could not form. Yet this clearly did not happen. Observations show the dark energy density is extremely small, roughly 10 e circumflex letter 2c6 12 joules per cubic meter. By contrast, naive quantum field calculations predict values larger by a factor of 10,120. This mismatch is not merely large, it is the largest known discrepancy between theory and observation in all of science. This is known as the cosmological constant problem. It is not a technical issue, it is a crisis. The cosmological constant appears in Einstein's equations as a measure of vacuum energy. If vacuum energy exists and experiments show that it does, then it must gravitate. But if it gravitates as predicted, reality should not exist. Something is deeply wrong. Physicists have explored countless possibilities to resolve this contradiction. One idea is that vacuum energy contributions cancel out almost perfectly due to unknown symmetries. Another suggests that gravity does not respond to vacuum energy in the same way it responds to matter. Others invoke new physics beyond the standard model, but no solution has achieved consensus. One of the most troubling aspects of vacuum energy is its universality. Unlike matter or radiation, vacuum energy does not dilute as space expands. As new space forms, new vacuum energy appears with it. This makes it fundamentally different from any known substance. In cosmology, this behavior leads to exponential expansion. If vacuum energy dominates, the expansion rate approaches a constant value, and distances between galaxies grow exponentially over time. This is not hypothetical, it is exactly what current observations suggest is happening. The same mechanism is believed to have driven cosmic inflation, a brief period of rapid expansion in the early universe. Inflationary models rely on vacuum-like energy fields to explain why the universe appears flat, homogeneous, and isotropic. This creates a disturbing symmetry. Vacuum energy may have shaped both the beginning and the end of the universe, but unlike inflation, which ended, dark energy shows no sign of stopping. This raises a profound question. Is dark energy truly constant, or is it the remnant of a dynamic process that has not yet fully played out? If vacuum energy is constant, then the universe's fate is sealed. Expansion will continue forever. Galaxies will recede beyond causal contact. Stars will exhaust their fuel. The universe will approach a cold, dark, empty state known as the heat death. If vacuum energy can change, the outcome could be far more dramatic. Some models predict a gradual decay, slowing acceleration. Others predict catastrophic transitions, vacuum decay events, that could alter the laws of physics locally or globally. These ideas are speculative, but they emerge naturally when vacuum energy is treated as a physical entity rather than a fixed parameter. The danger of vacuum energy lies not only in its magnitude, but in its instability. Quantum fields can exist in metastable states, configurations that appear stable but can transition to lower energy states through quantum tunneling. If the current vacuum is metastable, a transition to a lower energy vacuum could occur spontaneously. Such a transition would propagate at the speed of light, altering physical constants and destroying all existing structure. There would be no warning. No signal could outrun it. This is not science fiction. It is a direct implication of quantum field theory applied to cosmology. While current evidence suggests our vacuum is stable on timescales far exceeding the age of the universe, absolute certainty is impossible. This uncertainty underscores the core problem. We do not understand the vacuum. Despite being the foundation of all physical processes, the vacuum remains one of the least understood aspects of reality. It sits at the intersection of quantum mechanics, gravity, and cosmology, precisely where our theories fail to unify. Dark energy forces us to confront this failure directly. If dark energy is vacuum energy, then controlling dark energy would require controlling the vacuum itself, a concept far beyond current technological imagination. It would mean altering the energy state of space, manipulating quantum fields on cosmic scales. At present, this remains firmly in the realm of theoretical speculation. But physics progresses by turning speculation into measurement, and measurement into control. The first step is understanding whether vacuum energy is truly constant or merely appears so within current observational limits, which leads to a critical turning point in the documentary. What if dark energy is not a fixed property of space but something dynamic, evolving, and responsive to physical laws we have not yet discovered? Section 5: Einstein's biggest regret and his possible redemption. The cosmological constant, I circumflex, and why Einstein may have been right for the wrong reason. At the center of the dark energy problem lies a symbol so small it once seemed disposable, the Greek letter lambda, I circumflex. It represents the cosmological constant, a term Albert Einstein introduced into his equations of general relativity in 1917. At the time, its purpose was purely pragmatic. Einstein believed the universe was static, neither expanding nor contracting, and his equations did not permit such a universe without modification. Gravity would inevitably cause collapse. To counteract this, Einstein inserted I circumflex as a repulsive term, a form of energy intrinsic to space that exerted an outward pressure, exactly balancing gravity. With this addition, a static universe became mathematically possible, but it was an unstable balance, requiring precise fine-tuning. A small deviation would cause expansion or contraction. When Edwin Hubble later discovered cosmic expansion, the need for a static universe vanished. Einstein reportedly abandoned the cosmological constant, calling it his greatest blunder. For decades, I circumflex was treated as a historical footnote, an unnecessary artifact of an outdated assumption. Then the universe accelerated. With the discovery of cosmic acceleration in the late 1990s, I circumflex returned not as a mistake, but as the simplest explanation consistent with both observation and theory. A constant vacuum energy density fits the data remarkably well. In modern cosmology, this model is known as I circumflex CDM, lambda cold dark matter. It is the standard model of the universe, but simplicity hides discomfort. The cosmological constant is not derived from first principles. It is inserted into the equations and measured empirically. Its observed value is extraordinarily small, yet non-zero. This places it in an uncomfortable position between classical gravity and quantum physics connected to both, explained by neither. What makes I circumflex so compelling is its behavior. A true cosmological constant has constant energy density and negative pressure. As the universe expands, matter thins out, radiation fades, but I circumflex remains unchanged. Eventually, it dominates all dynamics. This matches observations with striking precision. Measurements of the equation of state parameter, which relates pressure to energy density, consistently yield values extremely close to a circumflex letter 2C61, the exact value predicted by a cosmological constant. Within current uncertainties, dark energy behaves like I circumflex. This success raises a troubling possibility. Perhaps dark energy is not dynamic at all. Perhaps it is simply a fundamental constant of nature like the speed of light or Planck's constant, whose value we must accept without explanation. But physics rarely rewards resignation. The value of I circumflex presents an enormous fine-tuning problem. If it were slightly larger, cosmic expansion would have prevented galaxies from forming. If it were slightly smaller or negative, gravity would have caused early collapse. The observed value lies in a narrow range that permits structure, stars, and life. This apparent coincidence has fueled debate for decades. One response is anthropic reasoning. In this view, I circumflex takes different values in different regions of a multiverse. We observe a small value because only such regions allow observers to exist. This idea is controversial not because it is illogical, but because it is difficult to test. Another approach seeks dynamical explanations. Perhaps I circumflex is not truly constant, but the present value of a field slowly evolving over cosmic time. This leads to models such as quintessence, where dark energy arises from a scalar field rolling down a potential landscape. These models can mimic I circumflex today while diverging in the future. They predict subtle deviations in the expansion history and structure growth deviations that next-generation surveys aim to detect. Yet dynamical models face their own challenges. They require new fields not present in the standard model. They often introduce fine-tuning of their own, and they must avoid instabilities that conflict with observations. Meanwhile, modified gravity theories attempt to explain acceleration without dark energy at all. In these models, Einstein's equations are altered so that gravity weakens or changes behavior on large scales. But again, observational constraints are severe. Most such theories struggle to remain consistent with precision tests of gravity. As a result, I circumflex remains dominant not because it is satisfying, but because alternatives are worse. This situation forces a philosophical shift. Physics traditionally aims to explain constants by deeper principles, but I circumflex resists such reduction. It sits at the boundary of knowledge, demanding either new physics or new ways of thinking about explanation itself. Einstein's possible redemption lies not in foresight, but in mathematical honesty. His equations allowed I circumflex. Nature appears to use it, but whether I circumflex is truly fundamental or merely effective remains unknown. If I circumflex is fundamental, controlling dark energy may be impossible. Constants cannot be manipulated. They define the rules of the universe. If I circumflex is emergent, a manifestation of deeper quantum processes, then understanding those processes becomes the key. This distinction matters because it determines whether dark energy is passive or active, fixed or mutable. At present, observations cannot definitively distinguish between a true cosmological constant and slowly evolving alternatives. The universe appears consistent with I circumflex, but precision is still limited. This uncertainty keeps the question open. As cosmologists push measurements to higher accuracy, they are not merely refining numbers. They are probing whether Einstein's splendor is a fixed feature of reality or a temporary placeholder for deeper laws. If I circumflex changes, even slightly, it would signal new physics beyond general relativity and quantum field theory. If it does not, physics must confront the possibility that one of the most important parameters in nature has no deeper explanation. Either outcome is profound. And yet, the most unsettling question remains ahead. What if dark energy is not just a constant or a field but a fundamental property of space itself, woven into the fabric of reality? Section 6 is dark energy a force, a field, or space itself? Why scientists cannot agree on what dark energy actually is. By this point in the story, dark energy has been measured, modeled, constrained, and mathematically accommodated. Yet a fundamental question remains unresolved. What kind of entity is dark energy? Is it a force like gravity? Is it a field like the Higgs? Or is it something even more radical, a property of spacetime itself, inseparable from the geometry of the universe? This question is not semantic. The answer determines whether dark energy can evolve, interact, or be influenced in any meaningful way. It determines whether cosmic acceleration is an immutable feature of reality or the result of deeper physics still hidden from view. To approach this problem, physicists first ask the most intuitive question: is dark energy a force? Forces, in physics, arise from interactions mediated by particles or fields. Gravity is mediated by spacetime curvature. Electromagnetism by photons. The strong and weak forces by gauge bosons. Forces act on objects, transmit influence, and often diminish with distance. Dark energy does none of these. It does not pull or push individual objects in a local sense. Galaxies bound by gravity do not feel dark energy tearing them apart. Solar systems remain intact. Atoms are unaffected. Dark energy operates only on the largest possible scales, where spacetime itself dominates dynamics. This immediately disqualifies dark energy as a conventional force. What about a field? Fields are everywhere in physics. The Higgs field fills all of space and gives particles mass. Scalar fields appear in inflationary cosmology. Quantum fields underlie all matter and energy. This leads to one of the most actively studied ideas in modern cosmology: quintessence. In quintessence models, dark energy arises from a scalar field that permeates space and evolves slowly over time. Unlike a cosmological constant, whose energy density is fixed, a quintessence field can change rolling down a potential landscape much like a ball rolling downhill. If dark energy is a field, then its equation of state would deviate slightly from that of a pure cosmological constant. The pressure-to-density ratio would not be exactly a circumflex letter 2C61, but close. Detecting such deviations is one of the central goals of precision cosmology. Quintessence has appealing features. It avoids the worst fine-tuning problems of I-circumflex. It allows dark energy to emerge dynamically. It provides a framework for evolution rather than stagnation. But it comes at a cost. Introducing a new scalar field raises immediate questions. Why does it exist? Why does it interact so weakly with matter? Why does it have the precise properties needed to dominate only in the recent universe? These questions often reintroduce fine-tuning under a different name. Moreover, scalar fields are notoriously difficult to stabilize. Small quantum corrections can dramatically alter their behavior. Many quintessence models struggle to remain consistent with both particle physics and cosmological observations. Still, the idea remains viable and testable. But there is an even more radical possibility. What if dark energy is not something in space, but something about space? In general relativity, spacetime is not a passive stage. It is a dynamic entity with its own degrees of freedom. Curvature is not imposed. It emerges from the distribution of energy and momentum. The cosmological constant can be interpreted as an intrinsic curvature of empty space, a baseline energy level of spacetime itself. In this view, dark energy is not a substance or field, but a geometric property of the vacuum. This interpretation is deeply unsettling because it implies that acceleration is not caused by anything acting on the universe. It is simply what empty space does. If this is correct, then asking what dark energy is may be the wrong question. The correct question would be why spacetime has the properties it does. This perspective aligns naturally with general relativity, but clashes violently with quantum field theory, which predicts enormous vacuum energies. Reconciling these views remains one of the deepest unsolved problems in physics. Some researchers push this idea further, suggesting that spacetime itself may be emergent, not fundamental, but arising from deeper quantum structures. In such frameworks, dark energy could reflect properties of entanglement, information, or quantum geometry. These ideas are speculative, but they are not arbitrary. They arise from attempts to unify gravity with quantum mechanics, a task that has resisted solution for nearly a century. Another class of models blurs the line between dark energy and gravity entirely. In these theories, acceleration arises not from a new component of the universe, but from modifications to how gravity behaves on large scales. The equations of general relativity are altered so that spacetime responds differently to energy at cosmic distances. Examples include scalar tensor theories, FR gravity, and massive gravity models. In these frameworks, what appears as dark energy is actually gravity behaving in an unfamiliar regime. These theories are mathematically sophisticated and conceptually appealing. They eliminate the need for dark energy altogether, but they face brutal observational constraints. Any modification to gravity must reproduce general relativity with extraordinary precision in the solar system. Binary pulsars, and gravitational wave observations. Most modified gravity theories fail one of these tests. Others introduce instabilities or predict unobserved phenomena. So far, general relativity continues to pass every test except cosmic acceleration, and even there, it works perfectly if I circumflex is included. This brings cosmology to an uncomfortable impasse. Dark energy behaves like a cosmological constant. It shows no convincing signs of dynamics. It does not clump, it does not interact, it does not evolve measurably, and yet its value makes no sense within known physics. This tension has led some physicists to consider a disturbing possibility. Dark energy may not be explainable within traditional frameworks at all. It may represent a boundary condition of the universe, a parameter set at the birth of spacetime. If so, then dark energy is neither force nor field. It is a fact, but before accepting that conclusion, science demands more data. Precision surveys are now measuring expansion history, structure growth, gravitational lensing, and cosmic geometry with unprecedented accuracy. Tiny deviations from I circumflex could reveal dynamics. Even null results are informative, because if dark energy truly is constant to all measurable precision, it will force a reevaluation of how physics explains constants, and whether explanation itself has limits. And if it is not constant, if it drifts, oscillates, or evolves, then something profound is happening beneath the surface of reality. Either way, the implications are enormous, because once the nature of dark energy is understood, the final question becomes unavoidable. What does dark energy mean for the ultimate fate of the universe? Section 7: What dark energy will do to the fate of the universe. How cosmic acceleration determines how everything ends. Once dark energy became dominant, cosmology stopped being only a science of origins and became a science of endings. For the first time, physicists could not only reconstruct the past of the universe, but also predict its long-term future, not in philosophical terms, but through equations tested against observation. The fate of the universe depends almost entirely on one factor: how dark energy behaves over time. Even small differences in its properties lead to radically different outcomes. The universe's destiny is not determined by stars, galaxies, or even dark matter, but by the physics of empty space. To understand why, it is necessary to appreciate a crucial transition that occurred roughly 5 billion years ago. Before this epoch, matter dominated the universe. Gravity controlled structure formation. Galaxies grew, clusters assembled, and cosmic webs thickened. Expansion continued, but it slowed. Then dark energy overtook matter. From that moment onward, expansion began to accelerate. This marked a permanent shift in cosmic dynamics. Matter has been losing influence ever since. If dark energy is a true cosmological constant, fixed, uniform, and eternal, then the universe is headed toward a scenario known as the Big Freeze, sometimes called heat death. In this future, acceleration continues indefinitely. Galaxies beyond our local group recede faster and faster until their light can no longer reach us. The observable universe shrinks, not because space contracts, but because expansion outruns information. Over trillions of years, star formation declines as gas is exhausted. Existing stars burn out. Black holes slowly evaporate through Hawking radiation. Eventually, the universe approaches a cold, dilute state of maximum entropy. Nothing dramatic happens at any single moment. Instead, everything fades. This outcome is not speculative. It follows directly from Ice circumflex-dominated expansion and the second law of thermodynamics. It is the most conservative prediction, and currently the most likely, but it is not the only possibility. If dark energy is dynamic, if its density changes over time, the future becomes far more uncertain. One possibility is phantom energy, where the pressure of dark energy is even more negative than that of a cosmological constant. In such models, dark energy density increases over time instead of remaining constant. This leads to the most violent cosmic ending ever proposed, the Big Rip. In a Big Rip scenario, acceleration becomes so extreme that it eventually overcomes all binding forces. First, galaxy clusters are torn apart, then individual galaxies, then solar systems. Eventually, even atoms are ripped apart as spacetime expansion overwhelms electromagnetic and nuclear forces. The timeline depends on how extreme the phantom behavior is. In some models, the end occurs tens of billions of years from now. In others, much sooner. Current observations do not favor phantom energy, but they cannot yet rule it out completely. Another possibility lies at the opposite extreme. Dark energy could weaken or decay. In such models, acceleration slows, stops, or reverses. If dark energy fades, matter may once again dominate. Expansion could approach a steady state, or even turn into contraction. This opens the door to scenarios like the Big Crunch, where gravity eventually halts expansion and causes the universe to collapse back into a dense state. However, current measurements strongly disfavor this outcome unless dark energy behaves very differently in the future than it does today. More subtle possibilities exist. Dark energy could oscillate, leading to alternating periods of acceleration and deceleration. It could decay into other forms of energy. It could trigger phase transitions in spacetime itself. One particularly unsettling idea is vacuum decay. If the current vacuum state is metastable, not the lowest possible energy configuration, then a transition to a lower energy vacuum could occur spontaneously. This would fundamentally alter physical constants, particle masses, and forces. Such a transition would propagate at the speed of light. Everything inside the bubble would be destroyed or transformed. There would be no warning, no signal, and no escape. This is not science fiction. It is a direct implication of quantum field theory. However, calculations suggest such events are extraordinarily unlikely on cosmological timescales. Still, the fact that they are possible at all illustrates how deeply dark energy is tied to the structure of reality. Dark energy also reshapes the observable universe in more immediate ways. As expansion accelerates, fewer galaxies remain observable. Over tens of billions of years, distant galaxies disappear beyond the cosmic horizon. Future astronomers, if they exist, may see only a small island universe surrounded by darkness. This has implications for cosmology itself. Evidence of the Big Bang, such as the cosmic microwave background, will eventually fade beyond detectability. The universe will appear static and empty. Ironically, cosmic acceleration erases its own history. Dark energy also suppresses the growth of structure. Galaxy clusters stop forming. The cosmic web freezes in place. Gravity continues to act locally, but it cannot overcome expansion on large scales. This freezing marks the end of cosmic evolution as we know it. At a deeper level, dark energy raises unsettling philosophical questions. If the universe ends in emptiness, does complexity have an expiration date? Is the era of stars and galaxies a brief anomaly in an otherwise dark timeline? Current models suggest that the structured universe occupies only a tiny fraction of cosmic history. Most of time belongs to darkness. This realization forces a reevaluation of humanity's place in the universe, not spatially, but temporally. And yet, all of these outcomes hinge on a critical unknown. Does dark energy change with time? To answer that, scientists must detect tiny deviations in cosmic expansion, deviations so subtle they require observing billions of galaxies with extraordinary precision. This is why the future of cosmology is observational. Next-generation telescopes are not merely mapping space. They are mapping time, reconstructing the expansion history of the universe with unprecedented detail. Because if dark energy is evolving, it will leave fingerprints in structure growth, lensing patterns, and distance measurements. And if it is not evolving, physics must confront the reality that the fate of the universe is governed by a constant whose origin we do not understand. But one final question remains, and it is the most provocative of all. If dark energy controls the fate of the universe, could it ever be influenced, manipulated, or controlled even in principle? Section 8. Can dark energy change over time? Why scientists are searching for cracks in the universe's expansion history. If dark energy is truly constant, then the future of the universe is largely predetermined. But if it changes, even slightly, then everything from cosmic fate to fundamental physics must be reconsidered. This possibility has become one of the most important questions in modern science. Is dark energy static, or is it evolving? At first glance, observations appear to favor constancy. Measurements of the equation of state parameter, which relates dark energy's pressure to its energy density, consistently cluster around a value of -1, exactly what a cosmological constant predicts. But precision matters. A deviation of even a few percent would signal new physics. Detecting such deviations is extraordinarily difficult. Dark energy does not produce light, particles, or radiation. It can only be studied indirectly, through its effect on the expansion of space and the growth of cosmic structure. This requires observing the universe across vast distances and deep time. The challenge is not simply measuring distances, but comparing different epochs of cosmic history with extreme accuracy. This is why cosmology relies on multiple, independent probes. Supernova measure distances. Baryon acoustic oscillations provide standard rulers. Weak gravitational lensing maps structure growth. The cosmic microwave background anchors early universe conditions. If dark energy evolves, these probes will disagree in subtle but measurable ways. Over the past decade, hints of tension have begun to appear. One of the most discussed is the Hubble tension, a discrepancy between the expansion rate measured locally and the rate inferred from early universe observations. Local measurements, based on supernova and Cepheid variables, consistently yield a higher value than those derived from the cosmic microwave background. This discrepancy has survived extensive scrutiny. Systematic errors have been hunted aggressively, calibration methods refined. Independent teams have confirmed the result. While the Hubble tension does not directly prove evolving dark energy, it raises the possibility that the standard I-circumflex CDM model is incomplete. Another area of interest lies in large-scale structure formation. In a universe dominated by a cosmological constant, structure growth follows a precise pattern. Some surveys have hinted at slightly weaker growth than predicted. Again, the deviations are small. Individually, they are not decisive, but collectively they motivate caution. Cosmology has reached a level of precision where tiny inconsistencies matter. This has driven renewed interest in dynamic dark energy models. These models introduce fields whose energy density changes slowly over time. Unlike a constant vacuum energy, such fields can respond to cosmic expansion. Quintessence remains the most studied example. In these models, a scalar field evolves under a potential, contributing a form of energy with negative pressure. Depending on the potential's shape, the field can mimic a cosmological constant today while changing in the past or future. Some models predict early dark energy, a small contribution present before recombination that alters the expansion history just enough to relieve the Hubble tension. These models are actively tested against cosmic microwave background data, but introducing dynamics comes at a cost. Dynamic models often require careful tuning to avoid conflicts with observation. They must not disrupt nucleosynthesis, distort the cosmic microwave background excessively, or introduce instabilities. Many fail under scrutiny. Moreover, no compelling particle physics candidate for such a field has been confirmed. Another approach treats dark energy as an emergent phenomenon, a consequence of averaging inhomogeneities across the universe. In this view, acceleration could arise from the way spacetime curvature behaves when matter is clumped rather than smoothly distributed. This idea is mathematically subtle and controversial. Most analyses suggest the effect is too small to explain acceleration, but it highlights a deeper issue. Cosmology assumes large-scale smoothness, an assumption that may hide subtle effects. Still more radical are theories in which dark energy signals a breakdown of general relativity itself. In these models, gravity weakens or changes form on large scales. What appears as dark energy is actually modified spacetime dynamics. While elegant in principle, such theories are tightly constrained by gravitational wave observations and solar system tests. So far, none have decisively outperformed I-circumflex CDM. This brings us to a crucial point. Current data are consistent with a cosmological constant, but they do not prove it is fundamental. Cosmology is limited by noise, bias, and cosmic variance. The universe offers only one realization. Statistical certainty is hard-won. This is why upcoming experiments are so critical. The next generation of surveys, Euclid, the Vera C. Rubin Observatory, the Nancy Grace Roman Space Telescope, are designed to map billions of galaxies, measure lensing distortions at unprecedented precision, and reconstruct the expansion history across most of cosmic time. These surveys will not look for dark energy directly. They will look for inconsistencies. A changing dark energy would leave fingerprints, alter distance-redshift relations, modified growth rates, shifts in lensing statistics. Even null results will be transformative. If dark energy remains indistinguishable from a cosmological constant across all measurable epochs, physics must confront the reality that I-circumflex may be truly fundamental. This would deepen the cosmological constant problem rather than solve it. There is also a conceptual limit to what observation can reveal. If dark energy changes extremely slowly, its evolution may be undetectable within the lifetime of observational cosmology. In that case, humanity may never know whether it is truly constant. This possibility forces an uncomfortable conclusion. Some properties of the universe may be empirically inaccessible. Dark energy thus challenges not only physics, but the philosophy of science itself. And yet, the search continues not because success is guaranteed, but because the stakes are existential. Because if dark energy changes, even slightly, it opens the door to something unprecedented. The possibility that the universe's acceleration is not inevitable and that, in principle, it could be influenced, which leads to the most provocative question of all. Are scientists actually trying to control dark energy, and if so, What does that really mean? Section 9. Can dark energy change over time? Why the universe's fate may not be fixed. For nearly 2 decades after its discovery, dark energy was treated as a constant, unchanging, uniform, and eternal. This assumption was mathematically convenient and aligned with Einstein's cosmological constant, a fixed energy density embedded in the fabric of spacetime itself. But as observational precision increased, cosmologists began asking a dangerous question. What if dark energy is not constant at all? If dark energy evolves over time, then the universe's future is not predetermined. Expansion could slow, accelerate uncontrollably, or even reverse. This single uncertainty transforms dark energy from a passive background property into an active cosmic agent capable of reshaping the destiny of everything that exists. The key parameter in this debate is the equation of state parameter, known as W. This number defines the ratio between pressure and energy density of dark energy. A cosmological constant has W equals a circumflex letter C61 exactly, but observations do not measure W directly. They infer it statistically from supernova brightness, galaxy clustering, and cosmic microwave background fluctuations. And within the error margins, W might not equal a circumflex letter C61. That uncertainty opened the door to dynamic dark energy models. One such model is quintessence, a hypothetical scalar field that permeates space and evolves slowly over cosmic time. Unlike vacuum energy, quintessence has dynamics. Its energy density can rise or fall, depending on how the field rolls across its potential landscape. In some scenarios, quintessence weakens over time, allowing gravity to eventually dominate again. In others, it strengthens, pushing the universe toward ever faster expansion. Another possibility is phantom energy, where W a circumflex letter C61. This regime violates known energy conditions in general relativity, yet it is not strictly forbidden by observation. Phantom energy would cause the expansion rate to increase without bound, ultimately tearing apart galaxies, stars, planets, and even atoms in a hypothetical end state known as the Big Rip. In such a universe, time itself becomes finite. Yet another framework proposes early dark energy, a small but significant dark energy component active in the early universe. This idea has gained attention because it may help resolve the Hubble tensioned growing discrepancy between early and late universe measurements of the expansion rate. If dark energy briefly influenced the universe shortly after recombination, it could subtly alter cosmic distances without dominating today. Crucially, all these models predict slight deviations from the standard expansion history, deviations that are extraordinarily difficult to detect. The universe is vast, noisy, and governed by overlapping physical effects. Isolating dark energy's behavior requires statistical power on an unprecedented scale. This is why modern cosmology has shifted from discovery to precision measurement. Experiments are no longer asking whether dark energy exists, they are asking how it behaves. Subtle redshift distortions, weak gravitational lensing, baryon acoustic oscillations, and time-dependent clustering patterns all carry encoded information about whether dark energy is static or dynamic. If dark energy changes, even slightly, it implies new physics beyond the standard model and beyond Einstein's original formulation of gravity. It would suggest that vacuum energy is not a fixed property of spacetime, but an emergent phenomenon tied to deeper fields or dimensions. And that realization carries an unsettling implication. If dark energy can evolve naturally, then in principle, it can be influenced, not necessarily by humans but by physical processes, phase transitions, or interactions we do not yet understand. The line between measuring dark energy and interacting with it becomes conceptually thin. At this stage of the documentary, the story reaches a turning point. Dark energy is no longer just something the universe has. It may be something the universe does. And if that is true, the next question becomes unavoidable. Section 10. What would it mean to control dark energy? The most dangerous idea in modern science. For most of scientific history, the universe was something humanity observed, measured, and attempted to understand, but never something it could meaningfully influence at the largest scales. Dark energy challenges that boundary. If it is real, dynamic, and governed by physical laws rather than pure abstraction, then the concept of interaction cannot be dismissed outright. The question is no longer purely philosophical, it becomes physical. To be clear, no scientist today knows how to control dark energy, and no credible proposal suggests humanity is remotely close to doing so. Yet physics has repeatedly shown that phenomena once considered untouchable, electricity, nuclear energy, space-time curvature, eventually became subject to engineering. Dark energy forces scientists to ask, whether the same progression could ever occur again, and what the consequences would be. The first constraint is scale. Dark energy operates at the level of spacetime itself, with an energy density incredibly small by laboratory standards, yet dominant when integrated over cosmic volumes. To influence it locally would require manipulating vacuum conditions with a precision and stability far beyond anything achievable today. This immediately eliminates simplistic science fiction notions of turning dark energy on or off. If interaction is possible, it would be indirect, subtle, and governed by field dynamics rather than force. One speculative avenue involves vacuum engineering. In quantum field theory, what we call empty space is not empty, it is a seething structure of fluctuating fields, zero-point energies, and metastable states. The cosmological constant problem already suggests that vacuum energy is not fixed in the naive sense. If the vacuum can exist in multiple energy configurations, then in principle, transitions between them are possible. The early universe itself may have undergone such vacuum phase transitions. However, vacuum transitions are not gentle processes. A lower energy vacuum bubble expanding at near light speed would rewrite the laws of physics inside it, annihilating all existing structures. This is not a technology, it is an extinction-level event. The fact that such transitions have not occurred spontaneously in our observable universe places strong constraints on their likelihood, but not on their theoretical existence. Another line of inquiry involves scalar fields, such as those proposed in quintessence models. Scalar fields are central to modern physics. The Higgs field is a confirmed example. If dark energy is associated with a scalar field, then its behavior depends on its potential landscape. In theory, fields respond to boundary conditions, interactions, and coupling constants. The challenge is that any coupling strong enough to influence dark energy would almost certainly produce detectable effects elsewhere, effects we do not observe. This leads to an uncomfortable conclusion. Dark energy appears deliberately isolated from known forces. It does not cluster like matter, radiate like energy, or respond to electromagnetism. This isolation may be a fundamental property rather than a technical limitation. Dark energy may be protected by symmetry principles we do not yet understand. Still, scientists explore indirect control scenarios not as engineering proposals, but as theoretical stress tests. Could extreme spacetime curvature influence vacuum energy locally? Could artificial gravitational fields modify expansion metrics on microscopic scales? Could higher dimensional interactions, predicted in some quantum gravity theories, allow energy exchange between spacetime layers? At present, every serious analysis concludes the same thing. Any attempt to manipulate dark energy would require energies comparable to those that shape the universe itself. Stars, galaxies, even black holes are insignificant by comparison. Dark energy is not a tool, it is the background condition of existence. Yet the implications of even partial influence are staggering. A civilization capable of locally suppressing or amplifying expansion could, in principle, stabilize regions of spacetime indefinitely. Conversely, uncontrolled amplification could tear spacetime faster than light could escape, rendering causality meaningless. This is why many physicists argue that dark energy represents a natural limit, not just technological, but conceptual. It may mark the boundary between phenomena that can be engineered and those that can only be endured. And still, the human mind does not stop asking, because understanding always precedes control. The deeper truth is that this documentary is not really about controlling dark energy. It is about recognizing how small humanity is and how much of reality lies beyond intuitive experience. Dark energy dominates the universe, yet we cannot see it, touch it, or shield ourselves from it. It dictates the ultimate fate of all matter, yet it remains almost completely silent. Whether the universe ends in endless cold expansion, catastrophic disintegration, or a phase we cannot yet imagine depends on the nature of dark energy, and that nature is still unknown. In the end, the most honest scientific position is this: dark energy is not something we are trying to control. It is something we are trying to understand before it controls everything else.